up on the top of your screen,
Yeah, left
depending
arrow.
on how you have it leaved out, depending on how you have it laid out.
Okay, so I think you've been muted. I will be going through the core one code. I don't know, Don, if you wanted to start just from the top and go down or focus on the outer interpreter. But I will begin and I will just explain. I want to make sure that this is a good size too. So if you need me to zoom in more, let me know. Okay, so yeah, one of the main developments in the Core 1 was how it implemented the outer interpreter, which communicates with the dictionary, also communicates with our serial port through a UART. And this we have implemented using a state machine. So typically this will be implemented using CPU instructions like machine code. We decided to implement this in Silicon and see what results we'd get. So it's got a few states here that are defined here in this enum. Some of them have names that exist in Forth. The functionality might not be exactly equivalent. I came up with these names just to describe what made sense within the state machine. But I think some of my Forth background crept into there, and so they have matching names. So first thing we do is just set everything to known value, usually 0. This includes the control signals, includes the first state we're going to go to, which is idle, and includes the compilation state. So the default compilation state is interpret. I will come back to that in a moment. So when we start, there's no valid execution token. There's no input. There's nothing to execute. We're not accessing, the outer interpreter is not accessing memory. We're not writing to the dictionary. We're doing nothing. And we just set some basic control signals, including the UART. One thing I think is quite interesting is this pointer here. So WP is a word pointer. So it points to words in the dictionary. And I point it to the newest definition when it's in the idle state. So it's always ready to define or add some new code. And yeah, I found that convenient because it takes, I think, one cycle to access the dictionary and to get the read result. By the way, am I being highlighted or not in this meeting? That's fine. I think you can all hear me, so it's okay.
You're doing good.
Good. Right. So UART. So whenever we get something on the RX channel, we got a new byte coming in. What we do is we store that byte. We set this signal low UART receive, so it means that we're no longer going to receive any more UART until we process this byte. One thing I've added recently that wasn't in there before is actually an echo. So now I actually send it on the TX channel, and I have this signal here called send outer. The reason it's called outer is because the inner interpreter can also use the TX port. So I have two signals there, and there's some arbitration in another part of the code. So once we've received this byte, I'll give a bit more of a high-level overview now. So once we receive the byte, we then go to another state called parse, and that basically decides what that byte means. So one of the things we do is we check if it's white space, and I do that by checking if it's equal to a space or if it's somewhere between 10 and 13, which roughly equate to white space characters, including I think new line and or CR and line feed. Then, if it's not that, we have some other states depending on if it's a colon or it's the end of a definition. I will return to those later. Because the main thing that we do when we receive the character is we just put it inside a buffer here. So we have this array here called word in, and it's 32. So each, let's use the words carefully here. Each cell, because word means something in fourth, so I'm going to use the word cell. Each cell is 32 bits. And we have a number of those cells. So what I actually do is I pack the cell with bytes. So in this case, because it's 32 bits, I can pack it with 4 bytes. One of the reasons I do this is it makes the comparison quick and efficient later on, because we can compare 4 bytes in parallel. So if you've got 4 bytes here in your word in, and you read from the dictionary and that contains 4 bytes, you can just compare them all at once. It's really, really fast. And I think Chuck recommends this in programming a problem-oriented language, so I think that might have been where I got the idea from. Then we increase this counter here, which is pointing to the next index. And this word in, so the format that I use is that the very start of a string is the string length, and then after is all the characters. So I think that's equivalent to the C type strings, the C quotes strings in fourth, because the count is actually stored in the memory. So you in theory need to fetch that. The reason I decided to include it in there is it makes the comparison quick, because if 2 strings are different lengths, then that information is contained in the first cell. So since the information is in the first cell, you can quickly rule out if the strings are different, because they're going to have different lengths. So that's what we do here. It's the main activity. And normally after that, we would just go back to idle. Yeah, because the default state is idle. So we just go back to idle and we keep receiving from UART until we get one of these characters here, one of these white space or new line. So I will try to explain these now. So what we basically have here is another state machine within a state machine, which has a state called compilation. So there's a few different modes we can be in. The default one is interpret, which, I mean, I think interpret will always just go to here. So I'm going to just put something like interpret here so you can see. Otherwise, we have some different ones, like for colon. What would happen is we ignore the colon, and then we're looking for the definition. So if you have the colon and then the name of what you're defining, and then you have the rest of the code, this state machine is basically there to handle that. So it's all to do with compiling. And as you can see here, one of the bytes that can be recognized is colon. So compiling is literally built into the outer interpreter. This could change in the future. I might decide to make it an immediate word. I think, yeah, is it immediate? I don't know, like actually defined in the dictionary, like in traditional fourth. But the way this is structured is very easy to just do it in here. And we also have this semicolon, which is end compile. So let's go through some code that you might write, and I'll show you what the outer interpreter would do, and maybe I can show you what the inner interpreter would do too. So I'm going to come up with let me see, what's a real command? So on the core one right now, you can turn on the red LED by typing in red, and you hit the enter key, and then the red LED will turn on. So let's have a look at what happened in the outer interpreter. So of course we start in the idle state, we receive R. We would go to this state here, parse. So R is not white space, so we just skip all of this. And so we would put it into the buffer, into the word in buffer. Okay. Then we would receive E, is not white space or new line. So we go to here again, and it gets buffered. Then we write D, same thing again. And then finally, we hit the return key. Now, when we hit the return key, it's going to transmit, I think it transmits 13. So we're going to enter into this part here. The default compiling state is interpret. So we're interpreting. So we're going to go to this state here, before link. Now, before link seems a bit strange. The reason why it exists is essentially because of the delay that happens between updating the word pointer, that's pointing to the dictionary, and actually receiving the data. So what we basically do here is we're just allowing the data to be read from the dictionary. We can also update the word pointer in advance because, as I say, there's a delay. So you update this and you start reading the next one. And then we just go to the next state, get link. So what is the link? Well, if you know, a dictionary is in fourth is a links. Yeah, that's right. It's a linked list, basically, because the newest dictionary points to the next oldest one and the next oldest one and the next oldest one, all the way to the base, and then it stops. So that's exactly how we structured this. So that's the first thing we want to do. The way we structured the dictionary, I wish I could do a split screen here actually, but I don't know how to do it in Notepad. So maybe if I just scroll down briefly to the dictionary. So the way that entry is structured, let's just pick blue, for example. Here's the pointer. Here is the string. This is the count. That's in the first byte. Then we have the code, and then we have exit. That's it at the moment. That's all we have. It's a really, really simple format. So in get link, we're grabbing this 25, and as you see, 25 points to this next entry, which is green, and then green points to the next entry, that's red, and then this is the end of it, which is, I signify that with 0. So 0 is kind of like a null value in the core one. It means that you've reached the end. So let's pop back up and let's continue executing our word. Right, so we've got the link, so that's fine. We can now go to search. So what's search? Search is a bit of a weird name. It's more of a comparison. So we are now comparing the strings. So we have the string that we typed in, RED, and we're going to start comparing that with the entries in the in the dictionary. So that's basically what this is. Data bus is what comes out of the memory. It's just the data. And then you remember word in, that's what we parsed before. So we just check if they're equal. We can compare the whole 32 bits at once. If we parameterized it to 64 bits, it would be the same thing. And as you can see, that would make comparisons a lot quicker. If most of your fourth words are, well, red fits in one cell, so you only need to do one comparison. So really, really quick. And probably if not, it's going to be in 2 or 3. So you're talking about 2 or 3 clock cycles per lookup. Really, really quick. So yeah, that's pretty much what we do here. We just check if it's equal, and we move to the next cell. And how do we know when we found a matching definition? We know because we will be here. The reason we will be here is because we keep incrementing the cell. And if we've compared everything and everything matched, then we're eventually going to get to this statement here, because C cell is going to be greater than cells because we've compared all the cells together. I don't know what this is. I genuinely don't know. So I'll focus on the states. I can tell you what local XT is. So it means the execution token, which is basically equivalent to CFA in our system. I think I know what's happening here. So what's happening here is we're now pointing to the code. So by this point, after you've compared the string, remember the format was link, address, string, and then code. We're now pointing to the code. So that's pretty much what I'm storing in local XT. And because CFAs are always marked with a flag, in this case, our flag is that they're negative, they're less than 0, I do a negation here. So that's pretty much what's happening there. We're basically just picking up the CFA and putting it in local XT. In this case, this doesn't matter, but if there was no match and we got all the way to the end of the dictionary, we would basically okay, let me explain this better. So if there's no match for that dictionary entry, we go to the next. We go back to before link and it's going to continue. If we go through the whole dictionary and nothing matched, then we look to see if it's a number. This is actually the same as traditional fourth. And I'm not 100% sure of the origin. I believe that Chuck wanted everything to be redefined if you wanted. Even a number could be redefined that way. So I've just kept to that. But let's continue to see what happens with red. So we're going to go to a state called compile. Now you might think, well, hold on a second. We never wrote colon, so why are we going to compile? The reason we're compiling is because of the way I've designed the outer interpreter, which is that we always compile. We are always compiling a definition. It's just about whether it has a name or not. So yes, we don't really have interpretation as in the outer interpreter by default. We always just compile and then we decide to execute later. But when you add to the dictionary, the difference would be you store the name. So let me show you what happens. Compile. Here we go. Here's the state. So give me a moment. Okay. So we set this signal high here, dictionary write, which means we're writing to the dictionary. Because yes, whenever we compile, we are writing to the dictionary. In this case, what's happening is we're writing at the very end of the dictionary. So let me show you what that would look like. So there's a memory mapping that happens here, but I'll show for illustration. So imagine after here, for example, somewhere after this point, we are adding our compiled code, our CFAs. They're getting put one after another, after all the definitions. And then if we execute them and then we reset. So whenever we need a new definition, we add that. And any code that we're temporarily compiling will come before the last definition. So yeah, we're always writing to the dictionary. This makes it very easy to add new definitions because you just put the string in and then automatically you're going to add the CFAs. So that's how I managed to make, that's what part of the reason why I decided to add compile. It just covers two functionalities at once. So we've got dictionary, right? We're writing this execution token, resetting some values. This is a pointer for execution tokens. We increment it because we're writing a new one. Then we do something quite interesting.
Demitri, a quick
go on.
question. Execution tokens are the core one opcodes, right?
Execution tokens are that's actually a very interesting question. They don't have to be. It can just be a CFA. So I didn't really know the terminology of CFA before I worked in the core one. I only knew of execution token or XT. So you'll see XT used a lot, but in your mind you can think CFA. I'm thinking if it can be theoretically, yeah, it could be a native opcode too. Right now it wouldn't be, but there's no reason why it doesn't. It could easily be that. You can compile opcodes and you can compile CFAs. Right now we're just compiling CFAs, which is good maybe that I use the term execution token because we could use that to apply to both in the future. So it's a flexible naming as well. So let's have a look. So we now look at the byte in. We look at what was the last character we typed in because maybe it was just a space. Now here's the interesting thing. If it's a space, then we compile but we don't execute because we're probably going to type another word. So instead we just go back to the idle state. So yeah, so that's where you can write multiple words on one line, and you're just going to compile the XT or CFA for each of them. In this case, we hit the return key. So if we're in interpret state, which we are, because we're not creating a new definition, then we actually enter this state called add exit. Why? Because we're compiling, we're going to execute all of this code later on. So that what execute means is you're going to put your current address on the return stack and you're going to branch to the address of the code, all of these CFAs. But after you've executed them, you need to go back to what's on your return stack where you came from. So that's where add exit comes in. All of this makes nested definitions really easy. So that's all handled in this one state here. Let's have a look at add exit. Oops, maybe it's up. Yeah. Okay, I don't know why the state comes before it's used. So add exit, yeah, so that's it pretty much. So here, notice this is an opcode, exit. The actual exit opcode gets written in. We can mix CFAs with opcodes in core one. The reason for this is because we have a flag for CFA, so they can always be identified by the inner interpreter. So if the inner interpreter sees the flag, it will just say, okay, this is a CFA. I need to branch to that address and then execute the code there, or it will identify the opcode. So again, this is really convenient. So this exit, we can just compile in there. Then we do get XT. I have a note here that explains this state. Let's have a read. Repurpose for adding a delay for XT compilation before execute. Right. Okay. So this state, maybe it's worth renaming it. I'll see if Don gives me the thumbs up. But what's happening basically is we're only just setting the right signal for what's being compiled. So if we immediately went to execute, there would be no time for this code to be compiled. So this is basically just an empty state. It's just a delay. And it looks like what we're also doing here is we're deciding whether we need to execute or we're just going to go back to idle. This is because if you're making a new definition, if you're adding a new definition, you're also going to use this add exit state because every definition after the code is going to be exits. So but in our case, we're interpreting, well, quote unquote interpreting. We don't really interpret in the core one. So we now go to the execute state. The execute state used to do more than what it does now. Pretty much all it does is it says there is an execution token. Are you ready to execute? If so, great. Then it just goes back to idle. So it's pretty much just setting a flag, almost like a signal saying, hey, I have something for you to execute inner interpreter. And when the inner interpreter says it's ready, it will hand it over. That's pretty much all that's happening here. This means execution token write pointer and execution token read pointer. I don't think they're actually needed anymore, or they're used because we have exit. In the past, I think we needed to see when we had finished reading all of the execution tokens that had been compiled. But now it's going to happen automatically. We just execute them until we get to exit. And, well, I'll show you why that works in a minute. But, yeah, we don't need to worry about that. We just go back to idle state. So, yeah, that pretty much just sets the flag. Let's have a quick look now at the inner interpreter. Okay. In fact, I'm going to show you the boot ROM. So the only requirement really for the boot ROM, which does have a little bit of code for an interpreter, is that it starts with execute. Execute here is an opcode. When we finish executing, we branch back to execute. Now you might think, well, hold on a second. What if there's nothing to execute? Why do we just start in the execution state? Well, let me show you. The reason we can do this is because of how I designed the execute opcode. Again, it deviates from traditional forth here. It's a more flexible definition of execute because this is an opcode. It's not a word. So this is now the inner interpreter code. So when we're executing, what we do is we say we're busy. Now, what the busy flag does is it halts execution of opcodes, and you just keep executing this. So you just stay in this state. The reason is some opcodes take multiple cycles to complete. So we came up with the concept of the busy flag. So you can just set this flag, and then the opcode can take however many cycles it needs to finish, and then it will say it's no longer busy. And then it will, the inner interpreter can move on to the next. So we're going to say we're busy because why? Well, we need to check for something. We need to check whether there is actually an execution token ready for us. So whether there's a valid execution token. That was the flag that we set earlier in the outer interpreter. So the whole time, this would have been waiting. This is how we synchronize two processors. We have the inner interpreter and outer interpreter. And this is how we're synchronizing them. Execution token is valid. What do? We branch. So we're going to branch to where the first execution token was written. Yeah, that's all that means. We're no longer busy because now that we know where to go, we don't need to wait anymore. And this is a kind of internal detail, but we have this thing called skip op. What this is intended for is sometimes with an instruction, there's some data after it that we need to ignore. We need to actually skip the next thing that's going to be executed and create like a bubble. So that's what we're doing here with execute. I think the reason for this is basically the thing. So if you look at the, let me go back to here. It's a bit of pipelining here. So what we're doing is execute the program counter, if you like. It's not called a program counter in the core one, it's called memory pointer, but program counter is going to be looking at the next instruction, which is branch. So naturally, after execute, we would want to execute branch straight away. We'd want to do this and then branch. However, execute actually wants to take us to the code that we just compiled. So what this skip up will do is it's basically just going to cancel that branch instruction because we're not going to the next instruction, we're going somewhere else. If you like this, yeah, this is a sort of equivalent to flushes and stalls in a RISC-V, or yeah, it's like a RISC architecture. We don't really have, we've tried to keep away from pipelining in the core one, but these are two stages. We have one stage where we update the program counter, and then this is where we're executing because it's just, you can't do everything at once. So sometimes they need to communicate with each other. So that's why we're skipping that up. And of course we put, see, this is where we are right now. We put this on the return stack. And then we finally signal to the outer interpreter that we're ready. So a nice synchronization. We do all that synchronization. We then going to branch to the where the execution tokens have been compiled. And then probably what's going to happen, because they're CFAs, they would get handled in this state here. And all we do is we negate them again because they're stored with a negative flag. So we just remove the flag and we branch. That's it really. That's how we handle CFAs. It's really small piece of code. So yeah, that's exactly how we would do red. Hopefully it made sense. Sorry, before I move, are there any questions so far?
So I have a comment. When
Yes.
we first started Core 1, we called it boot ROM, but
Yes.
it's really, we should really rename that to like dictionary RAM, dick RAM or something.
Yeah, I think what happened was the boot ROM was meant to contain some very simple codes just to start up, but I realized I only needed 2 opcodes. The opcodes are so powerful that you only need 2, and so I started storing the dictionary in there as well. Although not quite. This here is actually when there's a compilation error. So we just emit this question mark. I would like OK to be in here too. I don't know why I've not implemented OK, but OK would probably be some code in here as well. And then, you know, the start of the dictionary can be anywhere.
So one other comment about this here. This is, think of this as microcoding. So let's say that you have, you know, 4 Core 1 processors. That means that the 4th computer has the interpreter and compiler. Core 1 processors are just like a microprocessor. So you can have multiple processors with their own boot ROM, and you could write code in this fashion to do something in complete parallel. All the Core 1s would be in parallel. You could have 10 of them, you could have 100 of them. It depends on how many LUTs you have. And these Core 1 cores are less than 1,500 LUTs. They're probably more like 1,200 on a different one, different FPGA. My other comment is this particular FPGA is really a cheap one. It's a $5 FPGA. And I talked to Lattice about it. They did not invent it. It actually takes twice as many LUTs to do anything. So when you see the number of LUTs used on this this FPGA, typically it'll be like 40% less on another FPGA. So Core 1 is using very few LUTs. I think we're down to what, 3,300 right now. And also I put in some SPI stuff. I'm going to strip all that out, and you'll probably gain back another 500 LUTs. So we have just a nice, clean fourth computer in Core 1. Later on, I'm going to be adding opcodes for doing SPI and that sort of thing, and that's what I had started doing earlier on in the project. That's why it's in the code.
Question. I didn't see it in the write-up, and I tuned in a little late. What's the elevator pitch for what this software does for a non-programmer who loves Forth? What is it for?
Okay, can you speak up a little bit?
Okay, I'm asking, what is the purpose of this code for a non-programmer who loves Forth?
The purpose is if you get the board and you download this code, you can program in Forth using the terminal program. So you use a USB to RS-232 cable, and like this one, and you can start playing around with it. What's interesting about this is this is like the NC 4000 or Chuck's Shaboom or the RTX 2000. You're literally designing your own chip. Literally, you could take this source code that we have, and you could take it to a foundry, and you could have a chip made. It would run 2 or 3 times faster, and you could put a lot more of them in there. You could put hundreds of processors inside.
Okay.
So if you want to compare it to green arrays, because the way they did it always uses less power than a standard FPGA. But regardless of power, it's going to use very low power. But the point is that you're literally playing around with Forth processor chip design.
Okay.
You for like $50.
One thing I'd like to chime in is also, because this is an FPGA, you can design your own peripherals.
Yes.
You what?
Whereas if, let's say, with my Zepto Forth on the Pico, or the RP2040 in general, I mean, you're limited to what they give you.
Correct.
But let's say, like the RP2040 has 2 SPI peripherals. But let's say you say, hey, I want a third one. Tough luck. Well, you can use the PIO, but that's a pain. But if you want them to work the same way as your other 2 SPI peripherals, you're out of luck. Whereas with this, because you are designing your own whole device
Processor.
at the hardware level, you can just, provided you have enough LUTs left, you can just make whatever you want.
You could have 100 SPI ports if you have the physical number of pins. When you look at FPGAs, you can get FPGAs with 700 GPIO pins. And yeah, that's a great point. You're not limited to what the processor designer thought, how many SPI ports you want, how many UARTs you want. You can expand your chip that's built around the Core 1 technology to have exactly the number of ports you want. And here's another thing. When you create a port in our system, you're creating a parallel process that can run up to 200 million operations per second. So you could have 100 SPIs all being hammered with 10 megahertz data, and it's not going to skip a beat. They're all going to be in parallel. And then the way you use that is you use a shared register. So when you create these little processors that are written in System Verilog, and System Verilog is very much like C code, as you've noticed. So it's pretty easy to understand. only one, because this is you're literally creating a circuit, right? Like 7400 logic circuit. You can't have two devices driving the same output. So what you do is you have an input and an output register on each one of these SPI ports. And so the fourth computer does a round robin and just stores the data it wants out on the port. And it doesn't have to stop and wait or anything. It just, the processor will pick up the data, squirt it out the port. And if data comes in, then it will update the port that the fourth computer can read. And so the fourth computer would be in a loop and reading and writing to like 100 SPI ports.
Don,
Yeah.
Don, I'd like you to wrap up around 10:30 if you can. So
Okay.
focus on that as a goal.
Demitri, is there anything you want to talk about before we sign off?
Great, yeah. Yeah, I support what you're saying there. And I mean, the reason why I got involved in, let's just say FPGAs and forth, I was already interested in FPGAs, but I was working in a different language called Oberon. And what I really wanted was to bridge the gap really between forth and not just hardware like a CPU, but hardware like LEDs and things like that on the board. Because what I found with other projects, and it's just the way things are normally done. To toggle an LED, you need to first write to this memory maps location to enable the GPIO pins, which do something. And it's very, very generic, where I just want to activate one signal. And so with the Core 1, we can have a definition like, I'm trying to find all my definitions here. There's quite a few. Not all of them are implemented, but one of them is LED. Here we go, IO LED. So we have an opcode for turning on an LED. Now that doesn't sound like a very big thing, but for me it was, because that's how I can test the board quickly and see, that it's working. That could be to operate a motor. It could be to write something to in a protocol like SPI. It can be any operation you like, really. And first we have the opcode. Then we can turn it into a word, so it's turned into the word LED. And then we can start using that in other definitions like red, green, blue. So now it's so easy to make that connection. And I can just type red, and look how short this is. This is like 3 or 4 cells.
Show them the definition for IO LED. It's really simple. This is how you.
Okay, in the interpreter, yeah.
Mm-hmm. This is how simple it is to create your own definitions. Look at that code. That's just
there we go.
So this is a list of all the opcodes that are, and typically when you create opcodes, it's going to be from 1 to 4 lines. Now, typically what you want to do though is you want to put a busy around it, like show an opcode that uses the busy flag.
Oh, there's a few. I think these are all. Oh, fetch does, but I won't review fetch. So fetch and store are in this version of the code we're working on, but if you're going to download the project, they're probably not there yet. This is because fetch and store use the outer interpreter, so I've had to add more states to the outer interpreter. But like, even if we look at something,
branch there. Yeah, let's look at it.
Even branch or. So first thing we do, branch is a bit of a funny one. Let's go for emit. Emit is because why does emit need multiple cycles? Because the UART is running at
19.2.
Yeah, 19.2. And the core one is running, at least on my board, is running at 12 megahertz. It can run faster, but that's the oscillator speed. So emit is going to take a long time to complete, comparatively. So the first thing we do is actually check, okay, is the busy flag false? The busy flag is always false by default. If it is, then we set it to true, because we know we're going to use multiple cycles, or we could use multiple cycles. That's interesting. Then we're telling UARTs that we want to send something from the inner interpreter. And then these can take however long they like. You see this busy here. So this is the UART being busy. So maybe the UART is busy for hundreds or even thousands of cycles. That's fine. We just stay here happily, keep doing this. And then when it's finished, when it's no longer busy, we're busy because we're an inner interpreter. But when UART's no longer busy, we say, okay, we're going to stop sending. And this is some stack manipulation. And then we're no longer busy anymore. So that's the last thing we do. And then as soon as that signal, because this is being driven by, is it blocking or is it not? Yeah, by a blocking assignment. What this means is basically, as soon as this will go low again, we'll start executing other instructions in the inner interpreter. So that's an example of how you can even have something that takes multiple cycles to complete in there. And we think this is a really helpful thing, because in RISC-V, for example, everything is designed so everything executes in one cycle. And then you end up with pipelining, which can be very complicated, very challenging to add to a pipeline. So this allows you to not have to worry about that and define your opcodes.
Demitri, can you show them plus, the opcode plus?
Plus.
Oh, one plus, one of those. Okay,
There we
because
go.
we had a question in the comments about, so these are your arithmetic. Look how simple that is. One plus, it's one line of code. That one line of code will probably run it at one clock cycle, which is like, if we had the clock at 200 megahertz, it's running at 200, but it's only running at 12 on this board. The board only goes up to 12. But so you can, and multiply it, this will do 32-bit multiplies in a clock cycle. So plus minus, shift will be one clock cycle. We're going to add division a little bit later on. I know we only have 2 minutes left. So anybody got a 2-minute question? So I guess that's the end of our talk. I thank you very much, Demitri. I know you're busy out there in UK land and you're 5 hours behind us.
Yeah, feel free to reach out to me if you have any questions with the core one. We're really excited to get this into your hands. And it comes from the place of just wanting to interact with hardware more easily. So I think when you see what you can do with that, especially in things like robotics, it's really going to make sense, how you can use the core one, how you can define new opcodes, and use them to make these really short but powerful programs.
And yeah, I'm very interested in Chris's talk. I can't stay for it, but I will watch the recording. Chris makes a huge point. It's so easy to debug your FPGAs using Core 1 or or Chris's method also, either one. It really makes it easier to learn FPGAs. So on that, thanks everybody. I have to personally go. We got another thing going on.
When you look at it, be sure to like it and comment on it, and subscribe to our YouTube channel. Thank you, Don. Thank you, Demitri.
Great
Travis,
talk.
good to go.
Okay. Well, I'm presenting about Zeptoscript, which the script is, if you look at it, you say, hey, that's for. But underneath it all, it is a high level dynamic language with garbage collection, which makes many things so much easier than doing them in fourth. For instance, okay, I'm going to share a screen and it's